This is an introduction to Module 5, in which we're going to look at higher order linear differential equations. So we're going to start here with sections 4.1 and 4.2. And again, we're looking at linear differential equations, but now they could be of order 2 or more. The first thing we're going to look at is the preliminary theory, and we're going to look at when do we know that we have existence and uniqueness. We'll see that we'll look at what we term homogeneous equations, and then what we're trying to get to is to a general solution. And I'll go a little bit over those things. And then in section 4.2, we'll talk about reduction of order. And there, what we're doing is if we have one solution, how can we get a second one? So an nth order linear initial value problem will look like this. You'll have some function of x times y to the nth derivative plus another function of x times y to the n minus 1 derivative, and so on until we have a function of x times y prime plus a function of x times y, and then we could have it equal to some function of x that is not being multiplied times y in any form. And then if we have n derivatives, we expect that we will have n minus 1 initial conditions, and they are listed here. And this is the type of problems that we want to study now. What we want to get to is the general solution and also determining existence and uniqueness. When do we know that this differential equation has a unique solution? And also, what is the general solution? What is the solution to this differential equation? We're going to begin in this section with homogeneous equations. You'll see we want to be able to understand and solve these homogeneous equations. And so again, this is the same equation as we had before, except that now it's set to 0. There's no term that has no y multiplied by it. One of the important things that we learn about these linear differential equations is that what's what is called the superposition principle. Meaning that if I have y1 and y2 and each of them satisfy the differential equation, then I know that the equation or the function y, which is a constant times y1 plus a constant times y2, also satisfies the differential equation. We're going to be interested in knowing what are fundamental sets of solutions. And that is exactly at n linearly independent solutions. So if we have a set like we have here, where we have n solutions, that's because it's nth order. So if it's second order, we need 2 solutions, and so on. And we need them to be what is called linearly independent. We will see that we have to first of all understand what does linear independence mean, and second of all, how do I find out whether the functions are linearly independent? For that, you will use a Wronskian, and this is just a picture of a Wronskian. You'll also have to know how to get determinants, and there's going to be a video that I will add that shows you how to get determinants for 2x2 and 3x3 matrices. Finally, once we have n linearly independent solutions for an nth order differential equation, then we can write what we call a general solution. As you can see, we've used the superposition principle in that we're multiplying C1 times one of our solutions, and then we have plus C2 times the next solution, and so on. And this comma here, that's a typo, so you can ignore that. So this is what we want to do. This is where we want to get to this general solution. Now, in section 4.2, we are going to focus on second order differential equations. And here we want to first of all write them in what is called standard form, where there's no term or no x function times the y double prime. And this is just a simple section in which we give you a formula. So if you know that you have one solution, say y1, then here's an equation by which you can find y2. You take e to this integral, you first do this integral, and then you take e to that power, and then you solve this integral here, use this formula, and you can find y2. y2 is also a function of x. I just didn't write y2 of x, but y2 will turn out to be a function of x. Once I have y1 and y2, because I have a second order differential equation, I have enough solutions and I can write the general solution.